Gitta from the University of Munich. She will talk about the mathematics of reliable AI. Thank you very much.
Yeah, thanks so much for the invitation. I mean, it's really a great pleasure for me to give a talk here. I'm sorry to not be there in person. I mean, I'm sure Miami is great, but it was not possible. So I think we all know how tremendous successful AI is these days, but on the other hand, we also know that there are serious reliability issues. And so with this talk, I would like to take you on a journey through the area of reliable AI from a mathematical perspective and show you what mathematics can actually contribute to that area. Now, I think if we look around us, I mean, we see AI, I mean, basically infusing our lives. We are at the beginning of the fourth industrial revolution through AI. I mean, we see self-driving cars, telecommunication, also legal issues are by now, to a certain extent, already decided by AI-based approaches, and then the whole healthcare sector. And so in that sense, what, as said, we are at the beginning of the fourth industrial revolution. I think what we will see over the next years is that AI will change our society in its full breadth radically. And so in that sense, I mean, there are also warning voices, people who are worried. And there was an interesting incident basically 6 years ago now, where one AI researcher won an award and he gave a plenary speech. And in this plenary speech, he claimed that machine learning, and so in that sense, artificial intelligence, is still at the level of alchemy. And his argument was that people don't really know which algorithms are better than others. Also, they don't really know how to set up the architecture of, for instance, neural networks in the correct way, and so on. And there was a big debate. I mean, in the end, I mean, people decided that, I mean, it's also important to drive theory further. Now we are 6 years later, and we can see where we stand. But you know, if you train a neural network, it's still a lot of trial and error. So in that sense, I mean, there's still this level of alchemy to a certain extent. So hopefully during the next years, when mathematics, I mean, involves these or infuses this area more and more, we will see a more and more rigid mathematical foundation. And in fact, I mean, there are also problems with reliability. So think, for instance, of problems with safety. There were already various accidents involving robots. Think of problems with security. One can hack into those systems, take over control, which is, for instance, a problem with self-driving cars, but also hospital systems. There are problems with privacy. These methods are extremely data hungry. And so privacy violations happen on a daily basis, basically, and problems with responsibility. So many of these decisions are black box decisions, and also often decisions are biased. So in that sense, it's fair to say that one current major problem worldwide is the lack of reliability of AI technology. But on the other hand, I mean, there are also regulations now. So for instance, I'm from Germany, from the European Union. We now have the AI Act of the European Union. And then also the G7 started the Hiroshima AI process when they met in Japan last year. So there are various initiatives to start regulations of AI and to make it more trustworthy. And from my perspective, I mean, what I would like to delve more into in this talk is to show you, I mean, what a profound mathematical understanding can contribute to reliability, because in a sense, I mean, you can only talk about reliable AI if you understand it really in its depths, and this requires, as we know, a mathematical understanding. So let me start slowly and give you a gentle introduction into what AI is about, in particular its workhorse of artificial intelligence. So, I mean, this is nothing new. It started in 1943 with McCulloch and Pitts, and their idea and their goal was to introduce artificial intelligence. And since we humans believe that we are intelligent, what they aim to do is they wanted to mathematically model the human brain. Now, the human brain consists of neurons which are interconnected. And so let me show you this picture. So what they did was, I mean, so what happens in a neuron is you get some signals in. This is x1 to xn. These might be amplified in these dendrites. These are these weights, W1 to Wn, let's say. Then everything is collected here in the soma. And so this is mimicked by just taking the sum over xi, wi. And then the neuron needs to decide whether to fire or not. And this is modeled by a bias term, which is compared to the sum. And then depending on whether it exceeds b or not, the neuron fires a 1 or a 0. So this is the most simplest way you can model a neuron in the human brain. And if you connect them, I mean, these are the free parameters. This is basically what is then adapted to the training data. Yeah, and so let's look at it in a bit more mathematical rigors. So an artificial neuron with weights W1 to Wn and bias B and an activation function. So let me make this smaller, and an activation function, which is a univariate function from R to R, is defined as this function f, which you see here. And you recognize from the previous slide the sum and the bias term. Now we have a bit more flexibility because we put an activation function on top, or we apply an activation function to it. And if you compare it to the previous slide, there the activation function was the Heaviside function, so we just had 1 or 0. But certainly this is too simplistic, and you could also think of others like sigmoidal function, which is a smooth function. But what is used these days is this spline, linear spline. It's a so-called rectifiable linear unit. It's just the max of 0 and max. Yeah, so basically from this sum minus b, you just keep the positive part and set the negative to 0. And for some reason, I mean, this for practical purposes seems to be sufficient. Okay, so now this is one artificial neuron. Now we connect those. You see this here. So all these yellow dots are the artificial neurons. And so what is the correct mathematical model for it? You see here, for instance, you get these two inputs to the first neuron, and this is this line. So this is more mapped, or this is multiplied with x1. This is multiplied with x2, which gives the first output. Then this line is encoded here. So this term times x3, and this line is encoded in here. So x is multiplied by this weight matrix. Then you add the bias term. You apply the activation function in here, and then you keep going. So again, I mean, you have to encode this in a matrix, which is this matrix. You add a bias term, and so on and so on. Now, so what you see is a neural network is a combination of affine linear terms and nonlinear activation functions. And so it's not surprising how the general formula looks like. You see that here, again, a combination of affine linear functions and nonlinear activation functions. And so what you see here is, I mean, what is important is these neurons are aligned in layers, and the number of layers coincides with the number of affine linear terms here. But I mean, in effect, and the key message here is a neural network is a rigorous mathematical object. So it's accessible to everything in mathematics. So what are the key mathematical questions? So for this, I would like to take you once through how you apply neural networks. A neural network is used for approximation purposes. You have a complex function, which you don't know. Maybe it's defined on a lower dimensional manifold, and maybe it's a classification function. So for instance, these could be images, and maybe here, I mean, computer scientists like to separate cats from dogs. So maybe all cats are mapped to 1 and all dogs are mapped to the value 2. What you just have at hand are sample values, so xi, f of xi. In this language, it would mean images and their labels. Okay, so from these samples, you want to learn an approximation of f. And the approximation, I mean, the ansatz function on neural networks. So what you do now is you split the sampling set in a training and a test data set. The test data set you set aside, you just use the training set. And the first, what you have to decide is how to set up your neural network. How many layers do you have? How many neurons in each layer? Which activation function? Maybe you don't want to have something fully connected, so you want to already at this point set certain entries of these weight matrices equal to 0. Once you have decided that, then you need to train. And training means solving this optimization problem. So let me walk you through that. What you see here, this is the neural network function. So remember, the weights and the biases are the free parameters. You apply it to the xi's, which you know, and you want that this is close to f of xi, which you also know. This is a loss function. It could be the square loss, for instance, and then you sum over all training samples, and then you optimize. And so a classical method to solve this is gradient descent. Now, gradient descent, you run into problems because you typically have 1 million training samples and you don't want to compute 1 million gradients. So in that sense, what people use is stochastic gradient descent, which does the following. It takes only, let's say, a selected part of training samples and only computes the gradient for those and thinks that this is a good average. Okay, in any case, if you've done that, then you have your neural network function and you then use your test data set to test how good it performs on unseen data. Yeah, so you expose, your neural network to xi's, which it has not seen before, and you hope that it's still close to f of xi. Okay, so that's the general workflow, and from this, the questions arise. The first, remember, we have to choose the architecture. So the first area is expressivity. It asks how to set up your neural network architecture in the best way from an approximation viewpoint. So areas which are involved here, approximation theory, applied harmonic analysis, and so on. It's maybe the most developed area so far. The second is learning. So why does stochastic gradient descent work so well, although the problem is highly non-convex? And so here people use also a lot of different tools, optimization, optimal control, also areas like algebraic differential geometry to understand the shape of these local mean. And then generalization, you want to have overall success guarantees on the test data set. So this goes usually into the direction of probability theory and statistics. Now, these three are the directions or the key components of the error of a statistical learning problem, because what you see here is the error from the hypothesis class, the error from the algorithm, and the out of sample. And then there's another area which is called explainability, which is very new. And this asks now the question, I have already a trained neural network. I don't know how it was trained, but I want to understand how it reaches decisions. And so this is key these days because a lot of regulations require the right to explain. Yeah, so the customer or whoever uses the neural network has the right to know if a decision is taken by a neural network, what are the key features of the input data. And so this uses information theory, uncertainty quantification. And then there's another area which is also very dear to my heart, which people are not that much looking at these days, but which I think is extremely important, are their fundamental limitations. And so I will also delve into this. So I'd like to show you a bit about generalization, explainability, and then finish with some final thoughts about limitations. So let's start with generalization. So the key question, or maybe the main mystery, is as follows. This is a picture from statistical learning theory, which is very well understood. So let me walk you through that. We have here the capacity of the hypothesis class. In our terms, it's the size of the neural network. And this is the error. Now, the larger the neural network, the better it fits the data, and certainly then the smaller the training error is. But the test error will at some point go up. And that's this phenomena which people call overfitting. And it's depicted here. You see, for instance, if you want to separate these two classes, these blue stars from these green dots, and if my network is not expressive enough, maybe it can just draw lines, and it will do a really bad job in separating those structures. If it's a bit more expressive, maybe it does something like this, which already looks pretty good because this green dot might be an outlier. And then if it does its job too good, it could do something like this. And then if you have a new point, it might be easily misclassified. And that's called overfitting. The network aims to do the job too good, and that's this curve. But what happens these days really is this figure. So you see this coincides with this, but now at some point the error goes down again. And this is why people say the larger the better. And so this is the so-called double descent curve. And people aim to understand this by a lot of tools, VC dimension, radar complexity, neural tangent kernels, and so on. So what I would like to show you here is one approach where we can actually solve part of the generalization problem, but from a deterministic viewpoint, from a functional analytic viewpoint. And this takes us to, I think, a very interesting area, not neural networks, but graph neural networks. So these are neural networks which do not act on Euclidean data, but on graphs. And this is a generalization because you can view Euclidean data also as a graph. But a graph is a map from graph nodes to RC. So basically, if you have a graph, I mean, at every node you have a vector, a feature vector. And so this is the input to the neural network. And each layer, remember the layer was before a weight matrix and an activation function. So for these graph convolutional neural networks, the weight is now, I mean, these are convolutions. The activation function remains the same. And then we have another layer, which is pooling, which basically reduces the dimension again because the convolution will expand. But I mean, this is not that crucial here for this, let's say, path we will take. These are applications, therefore graph neural networks are extremely interesting these days. You see here recommender systems, fake news detection, chemistry, all of those are graphs, and all of those are often used now, I mean, solved now by graph neural networks. So what we want to look at now, I mean, is this generalization question. You see, this is the general overall question. You have graphs unseen in the training set, and the question is whether the neural network could generalize to that. Yeah, so let's assume I have this graph on the right-hand side. It's not in my training data. This is in my training data set. But then I expose later on the neural network to this graph, which it has not seen before. And the question is, I mean, can it generalize to this graph as well? How does it perform on that? And here we have a special situation because, I mean, we have graphs which model the same phenomena. And I will make this clear in a moment. Yeah, and so if two graphs come from the same phenomena, they should, I mean, the graph neural network should have approximately the same repercussion on both graphs, should handle them in a similar way. And what we can show is we can show this transferability for a particular class of graph neural networks. Yeah, and so I said this convolution for graphs, if I go back, this convolution you can do, as we all know, through Fourier analysis, you can do in spatial domain, but you can also do it in Fourier domain. And so we will do that here in Fourier domain. We will set up this particular convolution, and this I would like to first explain to you, and then we will discuss what it means that two graphs mimic the same phenomena, and then prove that actually graph neural networks are transferable or generalizable. Okay, so maybe you're familiar with, so if you have a graph, you have a degree matrix, you have an adjacency matrix. I mean, this is fairly standard, but then you can define a graph Laplacian. This is just a difference, which is a generalization of the normal Laplacian Euclidean space, or not an extension. It's it's the analog in the discrete world, and you can also normalize it. So a graph Laplacian is a self-adjoint operator. We have eigenvalues and eigenvectors, and in a certain sense, these eigenvectors are frequencies on the graph. So you see this here, you see the eigenvectors, and this is drawn in a continuum manner so that you see the different frequencies. So here you have low frequencies, and here you have high frequencies. Okay, so now, I mean, with this, typically convolution is defined in this way. You have eigenvectors of your graph Laplacian, and then convolution is typically defined like this, where this is, I mean, a discrete sequence. Yeah, so you have here your graph signal, you have here the eigenvectors, and then you multiply this filter sequence and you sum it. If you define your convolutions in this way, you have a series problem, because first of all, I mean, you need to compute the eigen decomposition, which is extremely slow and even not feasible if the graph is too large. Also, you might want to use the Fourier transform for computing this, but there's no general FFT for graphs. But even worse, this will not work, because imagine if you have a graph and you perturb it slightly, then this should be certainly, I mean, modeling the same phenomena. Otherwise, it doesn't make sense. Yeah. So if you perturb it slightly, the graph neural networks should handle both graphs in a similar way. But what you see here is if you perturb it slightly, these eigenvectors might change a lot. But this remains fixed. So that means then the convolution operator has a very different output. So in that sense, I mean, this will not work. We need to do something smarter. And so what we use is functional calculus. Now, functional calculus, I guess most of you are aware of this, does the following. Instead of having, or let's say not instead, I mean, if you have a self-adjoint operator, it explains what it means to apply a function to the self-adjoint operator. And so then this is this formula, this is the normal spectral decomposition, and you can write then g of t in this way. Yeah, so if g is, for instance, a square function, it's t squared, but you can also choose g in a different way, cosine and so on. So it is a very general framework explaining and interpreting what it means to apply a function to an operator. In the case of a rational function, it is also clear how it looks. So now, I mean, the trick is to, instead of having, I mean, this discrete sequence associated with the convolution, to have a continuous object. Yeah, and so in mathematics, it's a general phenomena. If you are in discrete mathematics, often it's easier to go to the continuous world and prove things there and bring it back to the discrete domain. And so this is what we do here as well. Yeah, so instead of having here, I mean, now this discrete sequence, each convolution is now associated a function g. Yeah, and so this function now I apply to the graph Laplacian, and I get this formula. And this is now my convolution instead of this. So the, let's say, what you choose instead of these CJs here is here the function g. And you see this has a lot of advantages because first of all, it solves the instability problem, because if I perturb my graph slightly, these UJs will change a lot, but I mean the lambda j's too. So this counterbalances this, and this remains stable. But also it solves the computability problem, because if g is a rational function, I don't even need to compute the eigendecomposition. Okay, so these are now, I mean, the filters which we use. And what does it mean, modeling the same phenomena? It means, let me just read it here, if you have graphs which are discretizations of the same metric space, then those represent the same. And so there's this correspondence, then if in my metric space the distance go up, then the edge weight will go down. So I view graphs now as discretization of the same metric space. There are also other frameworks like graphones, which are limit objects of graphs, and you can say if you have two graphs which are from the same sequence to a graphone, I mean, then these model the same thing. But we will go with this. So now everything is basically explained in this figure. You have these two graphs. You want to push it through one of these convolutional layers, and you want to check how the performance compares. These come from the same phenomenon. Okay, so what you do is the following. You put on top, I mean, you have these metric space which overlies both of those graphs, and you put a function on top. Then you discretize these functions, you sample them, you bring them down on the graphs. Now you want to apply the convolution. So the G will be the same because you push it through the same layer, but the graphs are different, so the graph Laplacians are different. So this adapts it to the different graph structures. So you apply here G of lambda 1 and here of lambda 2. And now you want to compare, and you bring it now back to the continuum domain, and then you can compare. Yeah, so this is, I mean, how you compare the performance or the repercussion if you push now the two different graphs of the neural network. And so, I mean, you can do it, I mean, it's much more complicated than I indicated. The analog domain is now world space. The digital domains are these graphs as graph Laplacians. I mean, on the Borel space, I have my band-limited spaces. I have sampling operators, which brings it down to the graph to L2 of G. And then I have something which brings it back up. And so let me just show you, I mean, the first result, which basically compares if you push your graph through the neural network as opposed to what happens just on the continuum set. Yeah, and so what you want to then estimate is, you see this here, you have your signal, you sample it on the graph, you apply your filter, your convolution, and then you bring it back up. And you compare it to what if you just stay on the continuum side. And this error you can estimate by these two terms. And so this looks very complicated, so let me go back. So these two terms, this is the transferability error of the Laplacian. You see the F is here the identity. And here you see this basically, I mean, we call it the consistency error, but this is, I mean, if you have something on the continuous space, you bring it down and you bring it back up and you look at the error. Now, so, and this is the overall error, which you see here. You see, I mean, there are different terms involved, but basically this is the message. The transferability is estimated by two very precise terms. But then, I mean, you certainly would like to have the full result by pushing two different graphs with two different graph Laplacians now through your neural network. And so here you see the estimate in its full glory. So this is if you push graph 1 to the neural network, this graph 2, and this is the estimate. You see the number of layers comes into play, the dimension of the Pauli-Wiener space. You see here this epsilon, the delta, which is the estimate in each layer, and the d is the Lipschitz constant. Okay, so I mean, the main message here is, I mean, this is one result which shows that you can get rigorous error bounds for the generalization error in certain cases. But what we are still missing is this overall error analysis, which also prevents to use neural networks in extremely sensitive applications. Okay, so let me now, I mean, come to the second point, which is explainability. Now, explainability, I would like to show you an applied harmonic analysis approach, which we drove. Explainability in a nutshell aims to the following. I have input data, like for instance here, this number 3. So, and my neural network says correctly, this is a 3. So if I put this image in my neural network, it says this is 3. And then I want to understand, why did it say this is a 3? What are the key features of my input to let it give this conclusion? And so this explainability approach then puts like a relevance map on this image, which says, well, the neural network looked at these red dots to decide that this is a 3. And that makes a lot of sense, because these red dots are the openings here, and the openings distinguish a 3 from an 8. But then from a mathematical standpoint, you're wondering, I mean, what exactly is relevance? Can we also develop an optimality theory? What is our optimal relevance maps? And ultimately, I mean, the area is going to the direction of you would like to be able to communicate with such an algorithm like you would with a human about the reason for a decision. Now, we are very far from that. With ChatGPT, we are a bit closer, but still far. But I mean, also what one should know and understand is that if you use such an algorithm explainability to fulfill the right to explain, to fulfill legal requirements, then this approach has to be also reliable. So it has to also better have a substantial mathematical foundation. And so here I would like to show you one of such approaches which we developed, which is based on information theory, weight distortion theory. Now, information theory is about the following. You have two persons. Alice has a message. She sends parts of the message to Bob at a certain rate. Typically rate is small. And then Bob has to decode it. He will make an error, and that's the distortion. So there's a trade-off between how much you send, the rate, and the error of reconstructing the message, the distortion. You can now phrase this explainability approach in this framework. And you can do that in the following way. Let's say Alice and Bob both have the same neural network. And Alice has the original image. She sends parts of the image to Bob. And hopefully the relevant part. And now Bob has to bring this in his neural network to decode it. But I mean, he has only parts of the image. So he first has to bring it back to image size. And he does so by obfuscating with random pixels, for instance. And so then he will get a decision. And so the distortion now is the distance between those, which you see here. So now it's a trade-off between you want to have very few pixels which are relevant, so you have concise explanations, but also the distortion should be kept under control. And so that's the so-called weight distortion function, minimizing the number of pixels as opposed to, I mean, with a constraint that the distortion is, for instance, less or equal than epsilon. If you work in optimization, you know this you cannot compute, but you can relax it because it's NP-PP complete, but you can relax it to this optimization problem. You see again the distortion here, and the this number of pixels is replaced by the little R1 norm, which promotes also sparsity. So now every pixel gets a relevance score between 0 and 1, but you have here a very rigorous mathematical object, which you can also analyze with respect to different aspects. Okay, so this is, for instance, one example. you have here your image, the network says correctly this is a dog, and you see here all different explanations of different approaches. And this is ours, which has very concise explanation, saying the neural network looked at the head of the dog to reach that conclusion. Now, that makes also a lot of sense. And so you can also compare by comparing how the different approaches act if you compare the rate to the distortion. Okay, but then you can extend it. For instance, I mean, you can say, why do you obfuscate with these random pixels? That looks very strange. And also, why do you have, let's say, a relevance for every pixel? And you can extend this the first by using what is called generative adversarial networks or generative AI, by putting here around something in a natural string. But maybe more interesting is you can actually also use decompositions of the data. For instance, I mean, you know, three bases from applied harmonic analysis. There are a lot of other bases and representation systems like wavelet, for instance, a wavelet basis. You decompose your image into wavelets, and then you put the relevance score on the coefficients. And so this is very comparable to image compression. So for image compression, what you do is you have an input image, you compute, let's say, wavelet decomposition, you select the largest entries, then you replace the others by zero. That gives you the compression. That's the classical image compression. And now from this, if you reconstruct, you want to be close to your original image. Now for this approach, which we call Kutyniok, we do something a bit in the spirit of that. We have our input image, we compute a wavelet decomposition, we select the largest entries, we replace the others with random noise, and then we reconstruct. And the reconstruction will certainly never be close to the original image, but I mean, through the lens of the neural network, it will be close. So it's in the spirit of image compression. And then you can do nice things like this. So here, I mean, this comes from telecommunication. You have here the buildings of a city map. The red dots are cell phone users, and then you have this white area, which is a cell tower. And the network computes this black and white background, which is a so-called radio map, and it indicates how strong the signal is. You see here, it's really black, and so you also have a bad reception because you have a lot of buildings obstructing you from the cell tower. But then the network did something, I mean, seemingly wrong. Now I put this black area of bad reception here, although people standing here are in front of the cell tower. And so then you can ask, why did the neural network make this decision here? And the explanation is it based its decision on this object. And in fact, I mean, these cell phone users have a bad reception. And so what turned out later on was there was actually a building missing in the city map. So the network did something correct, but the data was faulty. And so with explainability approaches, you can find that out. And here, this is just a funny example. You can also find out what the network has seen to reach wrong conclusions. So here, for instance, you have this image, and the network said that this is a diaper, although it's a man with a dog. And here it says this is a screw. And now, I mean, I will overlay it with the explanation, and then you will see what the network has seen to reach that wrong conclusion. And so if I overlay this, you see this looks a bit like a baby, and the diaper is not far off, and so this looks a bit like a screw. Yeah, so this was a switch. And so this way you can reveal why the network has reached wrong decisions and counteract, and so we have also extension. And now let me, I mean, the last minutes come to the last part. I mean, are there actually fundamental limitations? And what we looked at is, so you have typically continuum type problems, but you compute things on digital hardware. So you break everything down to zeros and ones. And the question is, I mean, what limitations does this cause, in particular for neural networks? And so there's a very interesting theory, computability theory, which is very closely also to mathematical logic. And in a nutshell, I mean, a computable problem is one which you see here, from which the input-output relation can be computed on a digital machine for any accuracy. And what we could show is that, I mean, the solution of finite dimensional inverse problems, like for instance, I mean, which is typically used in also medical imaging, is not computable. And the model for digital hardware which we use is the so-called Turing machine. So Turing machine is a canonical mathematical model for a digital computer. And so the solution is not computable by a deep neural network, which is a huge problem. I mean, it's not a problem of the inverse problem, it's a limitation of the computability, I mean, on today's hardware. So basically it says we are using not the correct hardware right now. And so this causes several problems. I mean, that means we cannot find an algorithm which on this hardware gives us the solution for any given accuracy. So in that sense, I mean, the output of neural networks is not reliable, and it could point towards why we see these problems with instability and non-robustness for neural networks. Because imagine, I mean, also for self-driving cars, we are not as far as we actually thought with AI. Yeah, so we are still in a much lower class. Yeah, so what to do now? Well, I mean, also there mathematics can give us an answer, because, I mean, what we could show is that this becomes computable if we go to the analog world. Now, so if we go to mathematical models of computing, which are analog. So there's a so-called Bloom-Schupf-Smale machine from the inventors, yeah, Bloom-Schupf and Smale might be known, who introduced a mathematical model for analog machines, and for this we could show it's computable. And so that means that reliability in certain settings might require novel hardware, and there are very interesting directions in the sense of analog computing, like neuromorphic computing, biocomputing, quantum computing, which, I mean, I'm sure everybody has heard of quantum computing, but also neuromorphic computing is interesting. It aims to introduce hardware which is much closer to the human brain. It basically mimics the signals transferred in human brains by voltages. And so we could show this, I mean, for many problems, this computability issue, for instance, classification problems, the pseudo-inverse is not computable. Also, there are problems with partial differential equations to a certain extent, and also optimization problems. So it might be that if you really want to go to mathematically reliable AI, you need to do that by analog computing. And there's another aspect which I didn't talk about yet, is the energy efficiency. So these GPU clusters, I mean, need enormous amount of energy. And so if you read the newspapers, I mean, now Microsoft and so on, they even want to build nuclear power plants just for their GPU centers. And so, for instance, neuromorphic computing in such innovative novel hardware would also solve this problem. Yeah, and so we also, in fact, now founded a company, Ecologic Computing, which also goes in this direction. And so this is the picture which is taken, I mean, in a certain sense, from the decadal plan of the Semiconductor Research Corporation, I mean, in the US, from the Biden administration. What you see there is, you see here the world energy production slowly rising. And then you see here these curves, which is the energy you need just for communication. If you stick with GPUs and if you use CPUs. If you stick, sorry, with CPUs and if you use GPUs. But you see, I mean, what you observe is that, I mean, in, I don't know, 15, 20 years, we will only with the energy we need for communication have reached the world energy production, which you can imagine is a tremendous problem. Yeah, and so this is I mean, as a fundamental limit as it can be. And so therefore neuromorphic computing is a very interesting direction. And so let me just use also one slide to show you that you can adapt neural networks also to neuromorphic computing, which makes them also closer to the human brain. It's a slightly different model. Now the inputs are so-called spikes. What happens in each neuron is what you see here. I mean, you get these continuous signals arriving at this neuron, and it's building up. And at some point, it will have reached the threshold, and then it will fire in the next direction. So what you observe here is time is here also a component. Everything before was synchronous, now it's asynchronous, and so now the timing is important, so it becomes much more complex. But what we could so far show is that, I mean, these so-called spiking neural networks can be emulated by classical neural networks, but it also can be shown in certain cases that they are much better concerning their complexity. So in that sense, I mean, that which gives an indication of that they are much more energy efficient. Okay, so let me finish with some final thoughts. I think we live, I mean, very interesting times. We live, as I said, at the beginning of the fourth industrial revolution through AI. We see impressive performance of AI in real-world applications, but a mathematical foundation is largely missing. They're very exciting directions and also very diverse concerning the mathematical tools you need for those. Yeah, so expressivity is related to approximation theory, learning, analyzing the learning approach related to optimization, generalization, more on the statistical side, explainability. We delved a bit more into generalization, explainability, which, I mean, explainability needs, I think, much more mathematics than there is right now. And also I talked about limitations in that sense of caution with problems with computability on digital hardware. But I think in general, there are very exciting future perspectives for mathematical foundations, and the area needs also much more mathematics still. And let me also finish, because we talked a lot about reliable AI with a small information. In Munich, we now have a school, a Konrad Zuse School of Excellence, specifically for reliable AI. It's a structured master plus PhD program. It's between both universities there, the TU Munich and the LMU Munich. And you see here in the area also mathematical foundations is one key research field, and so the areas to train them in, let's say, AI, but also so that the students have an eye on the importance of AI's reliability. And let me stop here and thank you very much for your attention.